Okay. I'm very sorry if this sounds funny. I'm working with the sound and everything. And I'm sorry the picture quality is bad, but this is all I could put together this evening. So, hope it's helpful. If not, next time will be better, I promise. So, number 1 here says, the figure shows a motion diagram of a car traveling down a street. The camera took 1 frame every second. A distance scale is provided. Part A says measure the X value of the car at each dot. Place your data in a table showing each position and the instant of time at which it occurred. So for part A, I'm just going to do my table here like a normal XY chart. So time is my independent variable and position X in meters is my dependent variable. So at 0 seconds, which is over here where I'm starting, I'm at 1200 meters. So 0, 1200. After 1 second, I said I was about at 980. You may have a different number there, but it's not going to change anything drastically. At 2, I said I was at 820. 3 seconds, 750. 4, 700. 5, 650. 6 was 600. 7 was 500. Okay, now we're right here. 8 seconds was 300, and then I ended up at 0 meters here at 9 seconds. So there's your table for part A. Part B says make a graph of position and time, and it says do not connect your dots. So if we do that, here's my graph. Sorry, that's hard to see. This is my position axis. This will be my time axis. So we have T in seconds, position in meters. Remember, position is X. Don't get that confused there. So I labeled mine by 200. So I did 200, 4, 6, 8, 1,000, 1,200. And I went over 9 seconds. So this is 0 and 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I could have speeded my graph up, but I'm going to just stick it in the bottom here. Okay, so we're starting at 0. We are at 1,200. We want to put a dot there. At 1 second, I'm at 980, so it's right underneath there. 2 seconds, I'm at 820. 3 seconds, 750. 4 seconds was 700. Then we had 650. And then we were finally at 600. Then we go down to 500, which is right between here. And then we go down to 300. So 300 is here. And finally at 9 seconds, we are at 0. So that's all for number 1. Number 2 says the position graph of a dog slowly sneaking up on a squirrel, then putting on a burst of speed. So here's your position graph. For how many seconds does the dog move at a slower speed? Okay, that's not 2, that is sorry guys, I just read 3. I'm going to go ahead and do 3 then. So it's asking for what time period are we running at a slower speed? Well, for A, we have from 0 to 8 seconds. We're looking at our slope. Remember, slope or speed, we don't care if it's positive or negative. This is a lower slope, lower speed. So the answer to A is how many seconds? For 8 seconds, it moves at a slower speed. B says draw the dog's velocity and time graph, include a numerical scale on both axes. So here again, I'm going to draw my velocity and time graph. I never have a positive speed, so I don't really need that. I'm going to go ahead and label -1, -2, okay, and 1, 2, And I need 10 seconds worth of data. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is T in seconds, V in meters per second. So the first thing I have to look at my slope. So I'm going from, I need to look at this slope here. So I'm going negative 2 meters per 8 seconds. That is negative 0.25 meters per second, or negative 1/4 meters per second, and I keep that for 8 seconds. So on my graph, I want to draw that. Here's negative 0.25, right about here, and I need to keep that constant speed for 8 seconds. Now my speed increases. I'm just increasing to the left. So I go from 4 meters to 0 meters. So I just had a displacement of negative 4 meters over the course of 8 to 10, 2 seconds. So that is negative 2 meters per second. Here we have negative 2. So I'm going to go here 8 seconds and 10 seconds. There's my velocity graph. Sorry about that. Now we can do number 2. It says for each motion diagram, determine the sign positive or negative of the position, time, and velocity. So here, I said for A, X is on the left side of my 0, so that means my position is negative. Now my velocity, on the other hand, is we are moving to the right. We're just speeding up to the right because our arrows are getting longer. So my velocity is actually positive. For B, here again, I am below the 0. Think of it like a coordinate plane. If this is 0, this region is negative, this is positive, and this is negative. So here we have negative position, and that is X, and we have a negative velocity. Okay? For C, here look at my position. Each dot is above the 0, like on a coordinate plane. So my position at all times here is positive. My velocity, however, look at the direction of your arrows. That tells you the sign, and it's pointing down, so my velocity is negative. Here we are at number 4. It says a mail carrier is driving slowly, putting mail in the boxes. He overshoots one, stops, shifts into reverse, and then backs up until he's at the right spot. A says draw the position and time graph. Here we're given the velocity and time graph. It says assume that X equals 0 and T equals 0. So the first thing I want to do is get my axis labeled. Okay, so you can see here I went up by 3s on my axis. That is because for 6 seconds I go 3 meters per second. So I need to show on my position graph a slope of 3 over 1 for 6 seconds. So I'm going to go from here. Since it tells me I can assume that everything is starting at 0, that's why I'm starting here. I'm going to go up 3 over 1, up 3 over 1. And I'm going to keep doing that until I get to 6 seconds. Now next, here we have a velocity of 0 from 6 to 8 seconds. Nothing's going on. I don't have a positive speed or a negative. So that means that I've stopped. So from 6 to 8 seconds, I need to show a slope of 0. Finally, we have a slope or a speed of 2 meters per second to the left. So I need to show a negative slope of negative 2 over 1. So if I'm at 18, I need to go down to 16 over 1, down to 14 over 1. So there's my graph. Now finally it says what's the position of the mailbox. Since the problem tells me that we end up at the right spot, my position must be here at X equals 14 meters. And that's that problem. Okay, number 5. it says, it gives us a velocity and time graph. It just says, draw the corresponding position and time graph. Assume that x equals 0 at t equals 0. Now, I've already set up my axis here for you. The reason I did negative, go by -3s is I know that in 4 seconds, I did my area here, okay? This area is going to tell me how far I need to go or what my displacement is going to be over the course of those 4 seconds. -3 times 4 gives me an area of -12 meters. So that means in 4 seconds, I need to be here down at -12. And I'm going at a constant rate. That's a flat line. So I'm just going to go ahead and start here at 0 and do a line to -12. Now, the second part shows that I have a positive speed of 3 from 4 to 6 seconds. So for the next 2 seconds, I need to show a change in my displacement. So from 4 seconds to 6 seconds, this area is going to be 2 times 3, which is a positive 6 meters. That means that from 4 seconds to 6 seconds, I need to end up here. I need to go from 12 meters to -6 meters, or -12 to -6. Finally, for the rest of the time, my area of this portion is going to be 6 and 12, that is 6 by 1. So this is a positive 6 meters. So that means that I need to go from -6 to 0 meters in 12 seconds, actually. 11 and 12, I need to add that there. And there's my position graph. B says, what is the position at 12 seconds? I'm just going to look at my position graph right here. At 12 seconds, we are at 0 meters. So for B, you should have gotten 0 meters. For C, describe a moving object that could have these graphs. The book mentions something to the effect of a football player shoots left, and then right, at the same speed, and then maybe he walks his returning position. So you just need to think of an object moving left, right, and then continuing to move right, but moving a little slower. We have a bicyclist whose position and time graph is shown. What is the velocity at 10 seconds, 25 seconds, and 35 seconds? So basically you're just looking at the slope here. At 10 seconds, I'm talking this region of my graph, so I need to look at the slope. I'm going from 50 to 100, so I'm going up 50 and over 20. So for A, that gives me a slope of 50 over 20, which is 2.5 meters per second at t equals 10 seconds. For part B, we're talking about this section, that's 25 seconds. This slope is 0, so that means I have a speed of 0 meters per second at t equals 25. Finally, for C, we need to find the slope of this section. So I go from 100 to 0, so I just went -100 over from 30 to 40, so over 10. So I just went -10 meters per second at 35 seconds. That one was pretty easy. Number 7, in Major League Baseball, the pitcher's mound is 60 feet from the batter. So here's my mound. Here's my batter. You know this is 60 feet away. The pitcher throws a ball with a velocity of positive 95 miles per hour. How much time elapses? So I'm looking for time when the ball leaves the pitcher's hand until the ball reaches the batter. And so I know delta x is a positive 60 feet. Now I want to make sure I'm using the same units. So there are 5,280 feet in 1 mile. So feet cancels here, and I'm left with 0.01 miles. being my displacement. Now you just know that time equals delta x over my velocity, because velocity equals displacement over time, and these two variables, algebra trick, they just switch. So you have 0.01 miles in 95, I'm going to do that, miles per hour. The miles cancels, this hour goes on top, so we know our units are coming out right. That is 1.1 times 10 to the negative fourth hour. Now we want to get rid of that. We want to make something that makes a little more sense. So I'm going to multiply that by the conversion factor of 3,600 seconds per hour. If I multiply those, these hours cancel now, and my answer becomes a little more clear as far as t equal to 0.4 seconds. This next problem, we have two people leaving a city. One leaves at 8 and drives 50 miles an hour. The other leaves at 9 and drives 60 miles an hour. It says, who gets to San Francisco first? So we know here is LA, here is San Francisco. We know delta x for both of them is going to be 400 miles. It says who gets there first, so I'm just going to go ahead and figure out what time each arrives. So let's talk about Alan first. Alan's velocity is 50 miles per hour. And I need to find the time that it's going to take Alan. So I'm going to do delta x over my velocity. So 400 miles over 50 miles per hour. Miles cancel, so we're left with a good time. That's going to take approximately 8 hours. So if he's leaving at 8 a.m., it takes him 8 hours and he doesn't stop. He's arriving at 4 p.m. Same thing for Beth now. So Beth's velocity is 60 miles per hour. And so the time it takes Beth, we have the same displacement. So 400 miles for 60 miles per hour. Miles cancels. 400 divided by 60. You get about 6.7 hours. So Beth arrives approximately at 3:40 p.m. So obviously, to answer A, Beth arrives first. To answer B, it should be an H. To answer B, she has to wait 20 minutes, approximately. Number 10, guys, is basically the same. We have some distance of 125 miles. And this guy is going at two different velocities. One is 65 miles per hour. The other is 70 miles per hour. We're going to do the exact same thing that we've been doing. So the first time is going to be delta x over v again. So 125 miles over 65 miles per hour. That's going to take about 1.92 hours or 1 hour 55 minutes once you do that conversion. T2 is going to be 125 miles over 70 miles per hour. Now there are multiple ways of doing this, so don't get boggled down. This is 1.79 hours or 1 hour and 47 minutes. When you look at this, you should save about 8 minutes. Here we have a 5-kilometer race. I want to label this 0, 5. I know delta x in every case is going to be 5. One runner runs at a steady, I want to say V1 is 12 kilometers per hour. And V2 is 14.5 kilometers per hour. Again, it is just asking how long one is going to have to wait. After the math, you see that the winner is going to have to wait 0.08 hours, or about 4.8 minutes. For this problem, it's still the same idea. Now it says, how far from the finish line is the slower runner when the faster runner finishes the race? So, first of all, I'm going to figure out the time that the faster runner finishes the race, and then I would essentially plug that in to figure out the position of the first runner. So what I want to start out by doing is write position functions for each of my runners. So the function for my first runner is 11 kilometers per hour times time. The position function for my second runner is 14 kilometers per hour times time. Now, I need to figure out what time this person is at 8 meters. So kilometers per hour times t. Solve this, you get t equals 0.57 hours. Plug that in to this function, and you will get the position of the first person, 11 kilometers per hour times 0.57 hours, and you get their position as 6.27 kilometers. Subtract that from 8, and you get about 1.73 kilometers behind. Okay, last two. Sorry this is taking so long. So it says, we have a graph of the blood in the ascending aorta during one beat of the heart. Part A says, how far in centimeters does the blood move during one beat? So we're basically looking for this area here. So for A, this is a triangle. I'm going to do 1/2 base times height. So I get 1/2 0.28. Oh, sorry, 0.2 seconds. I'm looking at my work wrong. 0.2 seconds times 0.75 meters per second. So seconds over seconds, I get a displacement of 0.075 meters, or 7.5 centimeters. Part B says, assume similar data for the motion of the blood in your aorta and make a rough estimate of the distance from your heart to your brain. So that estimate, I would say, would be about maybe 30 centimeters, or 0.3 meters. So if we have 30 centimeters and each beat is 7.5 centimeters, then multiply this out and you get about 4 beats to get to your brain. Last problem, guys. Sorry, this has been a very long video. A car starts from 10 meters at 0 seconds and moves with this velocity graph. A, what's the car position at 2 seconds, 3 seconds, and 4 seconds? So we basically just need to find the areas, because that will give me the displacement. And if I know I'm starting at 10 meters, I can figure out what my final position is. So at 2 seconds, I'm looking at the area of this trapezoid here. So I'm going to do 1/2 the sum of my bases. So my base 1 is 4, my base 2 is 12, and 2. So that is 16, that area is 16 meters. Now when I add that to 10 meters, to get my total position, or my final position, that was going to be 26 meters. For B, it says 3 seconds. So now at 3 seconds, I'm looking at this full triangle here. So I'm just going to do 1/2 base 3 times 12. And I'm going to go ahead and add this plus 10 because I know that's what I need. When I do that, I get 28 meters. That's going to give me my final position at 3 seconds. At 4 seconds, well, I know that this negative area is going to cancel with this area here. So it's the first area that I found, which turned out to be 16 meters plus 10 meters to give you 26 meters. So that's at 2, 3, and 4 seconds respectively. B says, does the car ever change direction? Well, we're going at a positive speed here. All we're doing is slowing down. So this object is slowing down to a speed of 0 meters per second right here. Then we start to speed up in the negative direction. So we did change direction here at 3 seconds. And that's all of the video. Sorry it took so long. These will get better as we progress through the year. Good luck studying.